Hello, advanced chemistry students. This is Dr. Rogalski. We're going to take a look at Chapter 14, Mixtures and Solutions. We are not doing every topic in this chapter, so pay close attention to the ones we're covering. In this particular unit, I usually have a really fun Kool-Aid demonstration to show you, but you'll just have to imagine it. We're looking first at the idea of concentration. I think it's pretty easy to understand in that if you take 100 grams of Kool-Aid and you put it into a large glass, then it's going to have a certain concentration. But if you take that Kool-Aid and you decrease the amount to 50 grams and put it in the same size glass, you'll definitely have something that's not as strong or not as concentrated. So the idea of concentration isn't a hard one to understand. Hello, advanced chemistry students. This is Dr. Rogalski, and we're going to be working on Chapter 14, Solutions. And we're only doing parts of this chapter, so pay close attention to the slides and what we're covering. So that you don't spend time doing a lot of material that's extra. In chemistry, we have a number of ways of describing concentration. One is the idea of percent by mass. We've looked a little bit at something like this already. It would be the mass of the solute. Well, the solute is the stuff you're dissolving, divided by the mass of the solution. That would be the solvent, plus the solute. So another one is percent by volume, so the volume of the solute. Okay, another way of describing concentration is the percent by volume, where you are looking at the volume of the solute divided by the volume of the solution. Volume in this case would probably be in milliliters. And in the upper level percent by mass, you'd probably be talking grams for the units of mass. The most useful one of all is this one called molarity. Molarity is written by a capital M and is equal to the moles of the solute divided by the liters of the solution or the solvent. In most cases, the solvent we'll be using is water. So molarity, again, very important, moles of solute divided by the liters of the solution or the solvent. The moles, we already know how to calculate. We've been doing that for the whole year. And so that it's not hard to do. It takes a little bit of thinking. Another one that is useful, you'll see more in biology even, is something called molality, and that's the moles of the solute divided by the kilograms of the solvent. Again, the solvent oftentimes is water. And another way of expressing concentration, again, would be percent by mass. So the mass of the solute in grams divided by the mass of the solution in grams times 100. And percent by volume, the same idea, volume of solute divided by the volume of the solution. So again, those are two other ones. The most important and the most useful for chemists is the idea of molarity. Molarity is the moles of the solute, and molarity, notice, is big M. Moles of solute will be the N, moles of the solute, divided by the liters. And this should be in liters, the volume, divided by the volume, which is usually in liters. One of the useful applications of this idea of concentration is the dilution equation, which is one that we will take a look at in a few minutes. So this is a useful equation as well. The most handy things a chemist can do in the lab is to make up solutions with a given molarity. You're given, say you want a certain volume, half a liter of 1.0 molar sodium chloride solution. You would need to calculate how much sodium chloride you would have to weigh out in order to get a liter's worth of the appropriate concentration. Please watch the videos on the PowerPoint and also in the long distance learning folder. They show you how to make solutions with a certain molarity, and they also show you how to do dilutions. So those are both pretty useful to watch. We'll practice some calculations here on the determination of molarity. So these would be the kind of calculations you would find in this unit. In this first question, a student adds 4.5 grams of sodium chloride to 100 milliliters of water. What is the molarity of the solution? So the molarity is big M equals the number of moles of sodium chloride divided by the liters of solution. 100 milliliters is 0.100 liters. So we're going to 0.100 liters. And we have to figure out how many moles of sodium chloride is in 4.5 grams of sodium chloride. So we need 4.5 grams of sodium chloride. You're going to have to calculate the molar mass, and I am going to run out of space here, so that's going to get a little tight. Molar mass is 58.45 grams per mole. That gives us 0.0770 moles. We had 2 grams, 4.5 grams of sodium chloride, so 2 sig figs, so we could round this to 2 sig figs, which would make it 0.078 moles. Okay, what we have to do now then is calculate molarity. We can carry the extra decimals and then round at the end. 770 divide by 0.100. The answer would come out to be 0.7. There's a I made a mistake up here, 0.07. So this is 0.0770 divided by 0.100, and that will give you 0.770 molar. This is 3 sig figs, so we might even want to round to 0.770 molar. Okay, and that's the answer for the first problem. The next question asks, how would you make a 1.5 molar solution of copper 2 sulfate in 1 liter of water? So we're going to start by figuring out how many moles that would be. So 1.5 moles per liter. And we're looking at 1 liter of solution, so 1.0 liters of solution. Units cancel. I need 1.5 moles. I have to look up the molar mass of copper sulfate. Molar mass of copper sulfate is 159.61 grams per mole. And therefore I'll have 1.5 0.5 moles. Divide by 159.61 grams per mole. No, actually I have moles on top. I want to have, yes, I don't want that here. I want this on top. This will be 159.61 grams per mole. The moles cancel, and the answer comes out to be 239.42 grams of copper 2 sulfate. We're looking at 2 sig figs, so 239. I would definitely not limit myself to 2 sig figs in this case. I would go ahead and measure out the 239.42 grams. And just to have the best accuracy in your solution, you would take that 239.42 grams and dissolve it up in a 1.0 liter volumetric flask for the best accuracy. In the next example, we have the question, how many grams of calcium chloride would be dissolved in 1 liter, 1.0 liters of a 0.10 molar solution of calcium chloride? Again, this is really dimensional analysis. If you think all the way back to the very beginning, we have, we have 0.10, write out molarity, moles per liter of calcium chloride. We're making 1 liter of the solution, and the molar mass for calcium chloride is 110.98 grams per 1 mole. And you should include all your units. I can't do it here, there's not enough space. But if you check your units, liters would cancel with liters. You'd have moles with moles over here, and then you'd end up with grams. And the answer comes out to be 11.098 grams of calcium chloride. And again, there's only 2 sig figs, but you wouldn't have if I were making this up, I'd want it to be as accurate as possible. And I would weigh out 11.098 grams of calcium chloride and dissolve it in a 1.0 liter volumetric flask. You should have seen one of these in one of the videos, but they're the best glassware to use if you want an accurate concentration. So that was the first one. In the next one, it says, what mass of sodium hydroxide is in 250 mils of a 3.0 molar sodium hydroxide solution? So we have 3.0, and please write out moles per liter, times 0.250 liters. So the liters will cancel, we'll have moles. And then we need to know the molar mass of sodium hydroxide. And so 1 mole of sodium hydroxide is equal to 40.01 grams of sodium hydroxide. If you cancel the units, the liters cancel, the moles cancel, and you obtain a value of, and let's see, Okay, 30.00 grams of sodium hydroxide. And in this case, you have 3.0 molar, that's 2 sig figs. The other one has 3 sig figs. And so the answer has 3 sig figs. Probably should be really only 30 grams of sodium hydroxide by the sig fig rules. But if you've got the equipment to make a better solution, more accurate solution, then you'd want to use it. Finally, the last one, very similar, although they give us the volume in mils at first, so there's an extra step, so we'll start with that. 1.5 times 10 to the minus 3 milliliters of a barium sulfide solution, and we have, so let's convert milliliters to liters right off the top, so 1,000 milliliters is 1 liter. The concentration is 10.0 molar, so 10.0 moles per liter. And then we also need to know the molar mass of barium sulfide. 1 mole of barium sulfide is 169.40 grams. Again, in the end, the answer comes out to be 2.59 times 10 to the minus 3 grams of barium sulfide. Okay, so those are a few practice problems here that we've done. I guess we've done 5. Most problems will be done in that way. I think the important thing to remember is to write molarity in terms of moles per liter. That'll help the dimensional analysis aspect of these problems stand out and guide you on the way. All right, one of the important ideas behind concentration is that you can take what is called a stock solution, which is very concentrated. So this would be a stock solution. And you can dilute it down to get solutions of lesser concentration. And we have an equation that allows us to do that. It's pretty easy. It's called M1 V1 equals M2 V2. You should memorize this. M1 will be the initial volume. Of the stock solution. Usually V1 will be how much of the stock solution do you need to use to create a solution. So M2 will be your final concentration. And V2 will be how much the volume you want to make. Okay. So basically, this problem says, what volume in milliliters of 2.0 molar calcium chloride stock? So really, this is our okay, so this is our stock solution. How many milliliters of 2.0 molar calcium chloride stock solution would you use to make 0.50 liters of 0.300 molar calcium chloride solution? So taking a look at this, 2 molar is our stock solution. We don't know how much of it we need to use, so that's in question. The final concentration is going to be 0.300 molar, and we want 0.5 liters. So M1 V1 equals M2 V2 we are looking for V1. How many milliliters of the stock solution do we need to make? So V1 is going to be equal to, we're solving for V1, so it'll be equal to M2V2 over M1. So we'll write that out. So 0.300 molar, so moles per liter. I can't write it all here. Times 0.50 liters. Again, if this had been given into milliliters, you would want to convert to liters. Divide by 2.0 molar, the stock solution. So if we go ahead and do that, V1, if you cancel the units, V1 will come out to have units of liters, which is what we want. So we come out with 0.075 liters or 75 milliliters. So what we would do in this case then is we would take 75 milliliters of the stock solution. We take 75 milliliters of the stock solution. We would put it into a volumetric flask, which would be 0.50 liters. So this would be a 500 milliliter volumetric flask. And in the end, the concentration that was in this volumetric flask would turn out to be 0.300 molar calcium chloride. Okay, so that's the process. The calculations are much the same. So this asks what volume of 3 molar Ki stock solution, potassium iodide, would you need to make 0.300 liters of a 1.25 molar potassium iodide solution? So again, we're going to have the formula M1V1 equals M2V2. And again, we're looking for what volume of the stock solution. So again, we're going to have V1 equals 1.25 molar. That's the concentration we're going for. We want 300 milliliters or 0.330 liters. And we divide by M1, which is 3.0 molar. That's our stock solution. Cancel units, you end up with liters, and therefore the final answer would be 0.125 liters of the stock solution. And again, you would take, this would be 125 milliliters of stock solution, transfer it right into the volumetric flask. This would be a, let's see, 300 milliliters volumetric flask. You would transfer 125 mils into here and then fill it to the top, right up to the line. Okay, here's another one. Same idea here. How many milliliters of a 5.0 molar? This is sulfuric acid stock solution. It's 5 molar. It's a very strong acid. Would you need to prepare 100 mils of 0.25 molar sulfuric acid? Using the same M1V1 equals M2V2 formula, again, we're looking for V1. We are looking for it in milliliters, so that's something to keep in mind. And we have V1 equal to 0.25 molar. We need 100 mils, so we put it into liters. You could leave this in milliliters if you want, in this case. because the units would cancel, or it doesn't say what, it does say what millimeters. We actually want milliliters, so we could use it in milliliters. Divide by 5.0 molar, that's the stock solution. So again, molarity cancels, and you have liters. It does say milliliters, so once we get the answer in liters, which would be 0.005 liters, we can go ahead and convert it into milliliters, which would be 5.0 milliliters. So we'd have 5.0 milliliters of our sulfuric acid stock solution. They would be transferred into a 100 ml volumetric flask, and then the flask would be filled to the line to give a total volume of 100.0 mils. So this is how you would do a dilution on sulfuric acid. Okay, this problem takes a little bit different, a different approach. It says if you have 0.50 liters of 5 molar stock solution of HCl, hydrochloric acid, if that is diluted to make 2 liters of solution, how many grams of HCl is in the solution? So again, we'll start with M1V1 equals M2V2. In this case, though, we need to find out how many moles are we talking about? What's the concentration in the diluted solution? And from there we can go on to find the number of moles and eventually the number of grams. Okay, so M1V1 equals M2V2. We are actually looking for M2 in this case. So we have M2 equals M1V1 over V2. That is equal to 5.00 moles per liter times 0.50 liters all over 2.0 liters. Liters cancel, leaving behind 1.25 molar or moles per liter. It says that we are making 2 liters. So in other words, we would need 2 moles, or 2 times 1.25. So I'll do that up here. We need 2 times 1.25 moles. And that gives us 2.5 moles of HCl. And the question asks for grams. So then we're going to have to multiply by the molar mass, which comes out to be 36.46 grams of HCl per mole. Finally, the answer for this question will be 91.15 grams of HCl. And sig fig wise, we do only have it down to 2, so you would round this up to 91 grams. 91 grams. Okay, so that's a little bit different take on the same idea. And then the next one says if you dilute 20 mils of a 3.5 molar solution to make 100 mils of solution, what is the molarity of the new solution? So again, M1V1 equals M2V2. We are looking at the molarity of the new solution, so we're looking for M2 equals M1V1 over V2. M2 then is equal to M1, which is the initial stock solution, so 3.5 molar. We're making 20 mils, so if we have 20 mils, we want to make 0.020 liters. And the new volume is going to be 100 milliliters or 0.100 liters. If you go ahead and cancel the units, you will come out with a value of 0.70 molar or moles per liter, and that would be of something unknown. We don't actually know what we have here. Very interesting. Okay, so that's those are some good examples of dilution calculations that you might see on an upcoming test. Another term that we want to be familiar with is just this idea of mole fraction. It is the ratio of the number of moles of solute in a solution to the total number of moles of solute and solvent. And it's basically given here. And this could be if you have more than one thing dissolved. The idea is here's solute A, here's solute B, and the idea of mole fraction simply is this is the moles of A divided by the total moles, and this is the moles of B, again divided by the total moles. So this comes in handy. We won't be doing too much of it in our calculations, but it is a good concept to have become familiar with. So mole fraction, it's exactly what you'd expect. Another important idea in this unit, one of the final ideas, is the idea of solvation. Solvation is a process by which solute particles interact with solvent particles to form a solution. So in other words, if I drop some solid sodium chloride into the beaker with some water, the sodium chloride, as we know now, will break apart into its ions, and the appropriate end of the water molecule will surround the sodium ions, and the appropriate end of the water molecule will surround the chloride ions. And again, this is an attraction between the dipoles of water and the ions of a crystal, and this is usually energetically favorable, and so you will have sodium chloride dissolving or being solvated by water. Solvation by water has a special term, and that's called hydration. It's useful for you to be able to draw pictures of these. That particulate diagram of these kinds of interactions are important to understand.